So when we purchase the racks, we will be specifying the size of the rack in units of U, 24U or 42U, like that. So what is mean by U? U means, one U means it is 1.75 inch. This is the size. So if you say my switch is 1U height, that means that my switch is having 1.25 inches of height. Okay. So if I say my switch is 5U, then it is 5 into 1.75 inch is my device height. So 42U means 42 into 1.75 inch. That much is the height of this rack. Okay. So this is the unit we are using. So we have switches which is of like 12U size. That means it's a big, like a fridge. And we have routers which is of 2U size also. So we cannot say that router is big or switch is big, right? It depends on what is the capability of the device. The size varies. All switches are not 12U. All routers are not 2U. There are different sizes. So the layer 2 or layer 3 is not defined based on the size. So switch is a layer 2 device and router is a layer 3 device and hub is a layer 1 device. Okay. So the reason why we classify it like this is it is based on our protocol stack. What is meant by protocol stack?
There's a OSI model.
OSI model. Yes. ISO OSI. Without ISO OSI, there is no networking, right? This is the very fundamental for any network engineer. Okay. All right. So ISO OSI defines 7 layers of communication, right? Physical layer, data link layer, then the uh, network layer, transport layer, session layer, application layer, right? So in this, your hub is working based on the information given in the physical layer of ISO OSI. Your switch is working using the information given in data link layer of ISO OSI. Router is working at the layer 3 of your ISO OSI, which is network layer information. So because of these devices, what is the basic operation they are doing and which layer information they are using to do their basic operation, based on that we classified them into different layers. Fine. So this is the reason behind the classification. So when we say data link layer protocol example is Ethernet. Network layer example is your IP, right? So Ethernet frame and IP packet. So if a device is doing his basic operation by, right, processing the Ethernet frame, then he is layer 2 device. If a device is doing his basic operation using IP packet, which is part of network layer, then that device we call him as a layer 3 device. So switches are using Ethernet frame for their basic processing, data forwarding. So switch is a layer 2 device. Router uses IP packet for doing the processing. That is the reason router is a layer 3 device. Hub don't have any intelligence. He will not look into anything. Whatever he receives, he will just blindly forward it to other port. It is like a cable, multiple cable connected together. Any voltage coming in one wire, one cable, it will go to all the other cables, right? So similar to that, hub is working. That is the reason we are calling hub is a layer 1 device. Got the logic? Any question? Okay. Okay. So inside our data center, this is my hardware. That is my server, and I have ESXi installed, and I'm going to run the VMs here. Now NSX-T provides a switching solution, okay, or a switching component. We can deploy multiple switches from NSX-T. Those switches are called segments. Segments are like, we can say, similar to, but not exactly same, similar to a VLAN. Or we can say these are a broadcast domain. Okay. So, or example, or in another way, we can say multiple devices part of the same network will be in one segment, or multiple devices part of one uh, network will be inside the VLAN. So VLAN and segments are similar. So the what is VLAN? Okay, if I have a
VLAN,
switch,
yeah, it's a broadcast domain again.
yeah, VLAN is a broadcast domain, or we can say a group of ports which can talk to each other. That is belong to a VLAN, right? Ports belong to different VLAN, they cannot talk. Same way, devices belong to a segment, they can talk to each other. Devices belong to different segments, they cannot talk to each other. Okay. All right. So in older versions of NSXT, the segments were called logical switches. So now the logical switches is renamed as segments. So when you say logical switch or when you say segments, it is same. Okay. So you can connect VMs to segments, you can remove VMs from segments, all those things are possible. How you connect your VM to a virtual switch on ESXi, similar way you can connect your VM to segments. So now uh, when you create a segment, there will be a VNID or VNI, VXLAN network identifier or VNID. Okay. For each segment, there will be a VNID allocated. So what is the range of VLAN? How many VLAN we can have in a network or in a switch?
4096.
Yeah. So 124096 is the maximum number possible, but in that two are reserved. So 4094 total numbers of VLAN you can configure.
Mm.
But the number range
Mm.
support is up to 4096. How about VXLAN? What is the number range?
The 16 million.
Million.
It is 16 million ranges are possible. That means 16 million networks you can create in VXLAN supported networks. And if you are using VLAN, you can get only 4094. Okay. So your segments are VXLAN backed. That means VXLAN is the logic behind the segments. So you can create 16 million segments. Okay. Practically, we will not do that many, but it supports. Okay. So when you create a segment, a VNID, VXLAN network identifier will be allocated, assigned to him. So for example, 5000 is the number allocated to this segment. If we create another one, 5001. So there will be different unique numbers will be allocated to each segment. Okay. So now
So
again,
the VLANs are assigned to segments.
no. VLAN is a different concept which we are not using generally in NSXT. Okay, just to
Mm,
make you understand the segment, I talked about VLAN because VLAN is
mm,
commonly used in networks, right? That is the reason I talked to you about VLAN, but we are not
mm,
using. VLAN is used where in the previous class we discussed the transport VLAN concept, right? A
mm,
VLAN on your network infrastructure through which your VXLAN encapsulated traffic will pass.
mm.
Okay, so that way we are using VLAN, and there is another scenario.
Shobkumar, I think,
Tell me. Hello.
yes, yes.
Tell me.
Yeah. I think we do not have VXLAN in NSXT, right? But we have only GNU.
No. We have a VLAN in NSXT. There are two cases. Okay. One we already discussed. I told you on your
Oh,
edge node, right? We discussed that,
yeah.
right? We have overlay transport zone and VLAN transport zone, right? The east-west traffic will come to edge, and when he send it to outside world, it will go as a VLAN traffic only. So this is one place where we will use VLAN. This we discussed already. Any confusion here? Okay. So the next case is the what to say, the migration scenario. What is this migration? Assume you have a traditional network and
Yeah.
you are going to migrate it to NSXT. So traditional network, you will have VLAN all over configured, right? Maybe you have virtualized servers also. In that case also we have vSwitches. vSwitches don't understand VXLAN. They are using all VLAN concept. Now what you are doing, the VMs running on those servers, you are migrating to a NSXT enabled data center. So how do you migrate? You have a segment here which is of 5000, and this is your traditional VLAN backdoor network. So if you want to migrate the VM to this segment, then we will use something called a bridging concept. So this bridge will act as a intermediator between your VXLAN supported network and your VLAN supported network. So here also we will use the concept of VLAN in one side, VXLAN in another side. This is a two scenario which I remember now. Okay, I don't remember any other case where we use VLAN.
Okay.
Clear?
Yeah, got it.
Right.
So
And
one side,
one, yeah, Vijay.
actually, this inside the NSXT, there is a VXLAN, and then when we are communicating with the VMs, we have a VLAN, right? That's what you meant to say.
This bridge
Mm.
is a NSXT component. Bridge configuration is a
Mm.
NSXT, right? So
So this
facility.
is the DVS or bridge?
No, it's all DVS now. Even your segment is
Mm.
a DVS now.
Oh, segment is
Previously,
DVS.
older versions, we were having a dedicated NVDS switch
Mm. Mm.
because
Mm.
DVS was not capable of doing NSXT functionalities. But now, in
Mm.
starting from 7.0 ESXi, even your DVS can function as a segment. They added NSXT capabilities to DVS switches by pushing those extra modules. They introduced that capability on DVS switches. All right. So even segment is also a DV switch. Your normal right port groups also DV switch. But when you use DVS for NSXT, he can do VXLAN capabilities on that DVS. But if you use a normal DVS, he don't understand VXLAN. That is the difference. Yeah.
Okay.
All right.
Yeah, I have one more doubt.
Hmm. Tell me.
Yeah, if IT team has created VLAN, so if I attached a port group to my VM with that VLAN, but it is not working, how can I check from ESXi and whether they are created VLAN really?
You cannot check.
Either from ESXi or DV switch.
You cannot check. That
Okay.
is the problem with your traditional network we discussed in the beginning, right? We need to log in into individual device to see what is happening there. From ESXi, you cannot check what is there in your physical switches. So only possibility is you ask them to share
Okay.
the configuration
But
or share them the output of some command.
okay, but we are talking in virtual. I mean, virtual environment, right? VLAN and
In
all.
virtual
No.
environment also, it is same. When you
Okay.
talk
Okay.
about SDN, you can see whatever is controlled by SDN. In one
Okay.
interface, if you log in, you will see multiple device details. But again, physical switch detail you cannot see because physical switches are not virtualized.
Hmm.
It is not coming under the control of SDN. Okay.
Okay. So whatever the VLAN is doing, the same thing VXLAN is doing, right? The only difference is it is doing encapsulation and decapsulation, right?
Yes. 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 Because of
Uh,
that, we are
uh,
getting a lot of additional
Apart,
features.
okay. Okay. For VXLAN, we have a lot of features, right?
Okay. In case of VLAN, we have something called a 802.1q tagging. It's a CCNA topic. Okay. Basic networking. So we on trunk links and all you might have heard about. Right, trunk links. In trunk link, what happens is whenever a traffic goes from part of a VLAN, it will add a extra header, extra field, which contains the VLAN information, which says, okay, this traffic is coming from this particular VLAN. Okay, that is only on trunk links it happens. So when it comes to VXLAN, we have the whole header is getting added. VXLAN header, then again TCP, IP, then Ethernet header is getting added. So that is the difference in the encapsulation. What extra is coming to the right datagram which is passing through the network. But if we talk about the capabilities, VXLAN give you a lot of other features because of this encapsulation, which is not
Okay.
available in VLAN. Okay.
How do we check this VLAN number in ESXi host? Is there any way?
VLAN number in ESXi, if you want to check, there is a possibility. We have something called a Wireshark. What about Wireshark? No. Okay.
Yeah,
So
yeah, sure.
Wireshark, uh,
Yeah, yeah.
Wireshark is a packet sniffing software. You can install it on any of your VM and you can capture the packets and you can see the content. Not only the Wireshark, there are many other packet sniffing softwares are available. You can install any one of them into your VM and you can see that.
Okay. Okay.
Okay.
So, one more doubt. That is from I think from class.
Hmm.
So, Shukmar, where this,
To
how this
avoid
we,
pair pinning, we create the large switch.
Kodishira, your voice is breaking. I didn't get you what you asked.
No, I was asking that to avoid hairpinning, we create the logical switch, right? So
No, 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 wrong,
suppose we have two VMs
wrong.
with different subnets.
Kodishra, Kodishra, what you said is
Oh,
wrong. To avoid
okay.
hairpinning, we didn't create the segments. Okay, to avoid hairpinning, we have the
Uh,
logical routers that we
okay.
didn't start discussing about it.
Uh,
Hmm. Ajay,
So
what
just
is it?
now we discussed that we can configure 4094 VLANs in one port group, right? But using NSXT, we can configure 16 million VLANs.
4094 4094 VLANs is not in one
VLANs.
port group, not in one port
Yeah.
group. We can have multiple port groups. Okay, each can have different number 10, 11, 15,
Yeah.
20, like that. Like this, I can have
Yeah.
maximum of 4094 VLANs.
Yeah. And also 16 million in VLANs in NSXT, right?
Yeah, if I am using VXLAN similar
So
to this, I can create 16 million. Yes. Hmm.
yeah, these 16 million VLANs will be configured in virtual world or physical world.
In your virtual switches, we are talking about NSXT, right? So on your NSXT,
Uh-huh.
you will create a
Okay.
logical, right? Finally, it is a port group only. Okay, if you look into the ESXi, it is a port group only like this, but these port groups are VXLAN enabled. So I can create 16 million port groups if I'm using NSXT. If I'm not using NSXT, I can create only 4094.
Where can we
Clear?
get it in virtual world? I didn't-
See, both are virtual world only, right? This DVS, if I use, this is also virtual. If I use NSXT, this is also virtual. This is also DVS. This is also DVS. But the difference is this DVS is not VXLAN capable. This DVS is VXLAN capable. When your device, virtual switch or physical switch, whatever it is, when it is VXLAN capable, then we are getting 16 million broadcast domain option. That's 16 million port group option. But when it comes to DVS without VXLAN, we can create only 4094 isolations, not the port groups. Okay, I can even have
Okay.
two port group with the same
And
VLAN number. That is possible.
yeah. Okay.
Hmm, tell me.
And NVDS get created automatically, or we have to create it?
NVDS will be created automatically. We did in the previous lab when we did our first lab. You created
Yeah.
you did a host preparation, right? When you do the host preparation,
Yeah.
we have an option of specifying the switch details. So when you do the host preparation, that time itself, the NVDS will be created. So NVDS is again, it is an older option. Now we have a choice whether you need a NVDS or you want to use a DVS. We can use both for NSX.
Uh-huh.
Previously, we were having only option of using
Okay.
NVDS for NSXT
And
functionalities. But now in NSXT, we can
yes.
say install a NVDS or we can say use a DVS switch for NSXT functionality. Both are possible.
Okay.
Yeah, Shivkumar, can you come up again? DBS.
See, when you do a host preparation
Hmm.
from NSXT manager,
Hmm.
you have an option to say
Hmm.
whether you want to use NVDS or
Hmm.
a DVS.
Okay.
for NSXT functionality.
Mm-hmm.
Okay, so it is your choice now. But in older
Mm.
version, only NVDS was the choice. It was not
Okay.
supporting, right, on
Mm.
DVS. Starting from
Okay.
vSphere 7.0,
Mm.
DVS is supporting.
Mm.
Any version before vSphere 7, choice is
Mm.
only in NVDS.
Okay. Okay, sir.
Okay, right. Okay, so you created transport zones, etc. Right, transport zone of overlay type and transport zone of VLAN type. So when you create a segment, you will say this segment is associated to this transport zone. So that means I can have segment associated with VLAN transport zone or overlay transport zone. So your segment is also of two type. Depends on where you are connecting. Segments can support overlay, that is VXLAN encapsulated traffic, or a VLAN traffic. Okay. So if you are creating a VLAN based segment, then the condition is this VLAN must be configured on your physical network also. So if it is a overlay network type, then there is no problem. Your network infrastructure already have a transport VLAN. So this traffic will be encapsulated and will be sent through that transport VLAN. But if you are configuring a VLAN segment, VLAN supporting segment, then how many VLAN supporting segment you are creating, that many VLANs must be configured on your physical switch, because there is no VXLAN encapsulation for this traffic. It will go as a plain VLAN traffic. I told you the scenario, right? So scenario is one, on your edge nodes, when the traffic goes out of your data center, that will be a VLAN type, or if you have a bridging configured. Okay. All right. So what are the choices we have as a transport node? One is you have ESXi, another you have KVM, right? So if you are using ESXi, then if you say you go with NVDS, then what is actually happening? This NVDS is actually derived from VDS. So they'll add some extra modules and we'll convert this VDS to a NVDS and they are using it. But now we have option, instead of VDS getting converted to NVDS, VDS itself with some support of modules, the same thing we can use. But here we are not using DVS with some modules, we are creating a completely new switch which is NVDS. But we have option of a DVS now. Now coming to KVM, if you are using KVM, then you don't have a choice of DVS. Why? Because DVS is CSXI capability, right? It's a vSphere feature or vSphere component is DVS. So if you are using KVM, then we don't have a choice of DVS. Then what is the next choice? It is NVDS. So from where NVDS is coming, we already discussed from OVS. I told you Linux uses Open Virtual Switch. So they are adding some modules into Open Virtual Switch and they are building the NVDA switches. Got the difference between networking part in ESXi and KVM, right? Any question here?
Mm. No.
So my question, I have a V switch when you install your ESXi. Then when I have vCenter server, when I create clusters and all, I can configure DVS. Now we are talking about a NVDS also. So can I have all these switches in the same server, or when I create one, the other should not be there? Any condition is like that?
I think vSwitch comes with the KVM, and then DVS NVDS comes with the ESXi.
No, vSwitch is part of ESXi. When you
But
first
there is a
install your ESXi,
hmm,
when you first install your ESXi, vSwitch 0 will
hmm,
be there. Part of installation to build the vSwitch 0. Right.
okay.
EVS you can create only when you have vCenter server, no?
Hmm, hmm,
So before you have a vCenter server itself, inside your ESXi you can have vSwitch 0. Even if you don't have a vCenter server, you can have vSwitch 0.
hmm,
And DVS is when you have vCenter server in your data center. And this can be used for NSXT. And NVDS is doesn't matter which vendor it is, whether it is a ESXi or KVM, doesn't matter, you can use NVDS. So this is only for ESXi.
hmm.
Okay. So you need to decide based on what you have in your data center. If you have ESXi transport nodes and if you have KVM transport nodes, then the best choice is going with the NVDS because you don't have much complexity. Both, right? On both we can use NVDS. But if I say DVS in ESXi and NVDS in KVM, then two type of networks I need to manage, no? So that will be difficult. So if you have only ESXi in your data center, then you can select this. If you have combination of both, then best to go with NVDS. Mhm. Hope there is no other question.
No, no, sir.
Okay. Now coming to NVDS. NVDS have two mode. Okay, so it is nothing big. If we have a standard mode and we have a enhanced data path. So when you do the host preparation, it will ask you what type of NVDS you want, enhanced data path or standard data path. Okay, standard type. So if you are using enhanced data path, then this is capable of doing network optimization. Okay, so if you need very high packet rate, low latency, low jitter, these are different properties of your traffic which is passing through your network. So if you are expecting any of these, if your voice traffic is passing through the network or any critical data is passing through your NVIDIA switches, then you will select enhanced data path. Otherwise, you can go with standard. And for enabling this, your OS or your hypervisor which is running must support DPDK, data plane development kit. So this is a um, enhanced software bundle we can say which gives all these functionalities. Okay, so depends on which hypervisor version you are using, you need to decide whether to use standard NVDS or enhanced data path mode. Okay, now let us see how it is working. Listen properly, at least for another 10 minutes. Okay, so assume I have two ESXi server. and I have my VM. And I have a segment created, segment 1. Segment 1. Segment 1 means it is a switch, right? Logical switch, which is accessible over all the host where it is mapped to the transport zone. So this overlay transport zone, this segment 1 is mapped or associated with your overlay transport zone. Now, as the overlay transport zone includes these two hosts, the segment will be accessible for these two hosts. Now, this VM I can connect to segment 1. This VM also I can connect to segment 1. Even if I am connecting them to the same segment, do we have a connectivity between these two server segment level? No, it should go through your physical infrastructure. This is your physical switch. So servers are connected to this physical switch. And when I say segment 1, this is actually segment 1 is visible here also. Segment 1 is visible here also. I'm connecting this VM here. I'm connecting this VM here. So this is how actual implementation. But logically, when we say, we can say segment 1 is spread across all these servers. That's why we are representing like this. I am drawing like this. But in actually, here we have segment 1, here also we have segment 1. So now how the traffic will flow from this VM. So you tell me what will be the subnet of this VM and this VM IP address range?
Same segment 1, right?
If they are connected
Broadcast
to
domains.
segment 1, they must be same
Same
network,
segment.
right?
Same
Same
network.
subnet 10.1, 10.2. It cannot be 10.1 and 11.1, not possible. Because one segment is one broadcast domain. They must be of same subnet. Okay. Now, this VM will send a traffic outside for destination 10.2. That will come and hit your segment 1. That is your virtual, right, NVIDIA switch. Now, what he will do is the traffic from 10.1 will be put inside your VXLAN header, right? And we have a transport VLAN defined. You did in the yesterday's lab, right? So transport VLAN is defined. For example, assume it is VLAN 10. So what he will do, he will add the Ethernet header with the VLAN number 10. So now this will go through this uplink, that is your cable, right? So what is this process called? Encapsulation. What encapsulation? VXLAN encapsulation. Who is doing that? When I discussed the host preparation, I showed you a VMK NIC with a VXLAN protocol stack enabled for that. So this VXLAN encapsulation is done by your host. That is the reason we call it as TAP or VTAP. So your host acting as VTAP and he is doing this encapsulation and it is sent out of your server. As it is VLAN 10 marked, it will go to the switch and he will send it to all the other ports which is configured with VLAN 10. So through this port, it will come here. When it comes to this segment or when it comes to this step, right here we have a TAP, right? TAP interface. So what this TAP interface will do is he will remove this VLAN header. Then he will remove this VXLAN header. At the same time, he will look into the value. What is this VXLAN number? I told you for each segment there will be one VXLAN number added, right? Allocated. So when he see the segment number 5000, he will send it to this segment. If he see 5001, he will send it to another segment, segment 2. So this is how they are identified. Got it? So even if you have a segment 2, how it will go? The path is same. VLAN will send traffic to the segment 2. Segment 2 will go to the TAP. TAP will do the encapsulation. But here, this time, the VXLAN number will be 5001. It will come through this. It will go here. Through which? Through the VLAN 10 itself. When it come here, this step will remove the header. The VXLAN header will be 10. VXLAN number will be 5001. So he will forward to the other segment. So even if you have 1000 segments created in your physical network infrastructure, what is a VLAN? Only one VLAN. VLAN 10 is what is significant here. Inside these servers, different segment numbers will make difference. It will decide where to which segment the traffic should go. Any question?
No, no. Nothing,
Simple,
okay.
right? There's nothing complex in
Mm,
this.
mm.
So only difference
You have
is,
any diagram to
sorry,
explain? You were explaining, but for reference, any
this is the
segment.
diagram now, right?
Uh, the VMware diagram, anything they explain. Okay, this is fine. Okay,
I
traffic flow.
don't have. Okay,
Okay,
this
okay,
is a
no problem, no
simplified
problem. Yeah,
diagram.
simplified.
This is a simplified diagram. Okay, because if you refer any other materials, then there will be a lot of information in one representation itself. So that's the reason
Mm-hmm.
I draw it with one single segment, then I expanded with the two segment, right? So ease of
Mm.
understanding.
So
In here,
here,
if you have,
yeah.
tell me,
So here, segment one. Suppose one VM is in segment one and another VM is in segment two. How it will communicate? It will go to
will it
router.
communicate? Tell me that first. A device in a VLAN, is it possible for him
Mm,
to talk to
no,
another
no, no.
VLAN member?
It's a logical switch, so it's not
Ah,
possible.
it is exactly similar to your VLAN. If you have a VLAN 10, you have 5 PCs. These 5 PCs can talk to each other. If you have VLAN
Mm-hmm.
20, if you have 5
Mm-hmm.
PC, these two 5 can talk to each other, but they cannot talk to
Mm-hmm.
each other. Different VLAN members, they cannot talk. Exactly same concept for segment, because these are
Mm-hmm.
broadcast domains. Different broadcast domain cannot talk to each other. Simple dot.
Mm-hmm.
Can I make them communicate?
No, right? Because
Can I
different.
make them communicate?
But we should have a router.
That's it,
Mm. Mm.
right? Same what we are doing for VLAN. For segments,
Mm.
different segments cannot talk to each other. Can I make them
Mm.
communicate? Yes. How do I do? Give a router there.
Mm.
Connect these segments to the router. Now different segments can talk to each other. Connect a
Mm.
router between different VLANs. Now different VLAN can talk to each other. Exact same process.
Mm. 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 No, no doubts at my.
Hmm. Okay. Kodisura, you are also clear, right? Okay. So every server will have a tab, obviously, and every server will do encapsulation, decapsulation, obviously. Those all I hope you already got it from this diagram itself, right? Okay. Now the question is, in physical world, on a physical switch, if I have a switch and if my PC is connected with MAC addresses A, B, C, switch is which layer? Layer 2.
Right.
So layer 2 means frames, Ethernet frames. In Ethernet frame, we have MAC addresses. So your switches can understand only MAC address, they don't understand IP address. So switches maintains a table called MAC table. Using this information, they are talking to each other. Okay. So how switch know about the MAC table? Because I'm just taking my laptop and connecting here. How switch will get to know about my MAC address? They have something called a MAC learning process. Whenever this device sends a data, from that he will learn. For example, assume A is sending something to C. So in the Ethernet header, source MAC address will be A, saying that A is sending the data. Destination MAC address will be C, and this PC will send it out. So it will come to the switch, this port number 1. So what switch will do is, he will take the frame and he know that he received the data on port number 1. So he'll make an entry in the MAC table saying that port number 1. And he will look into the frame. What is the source MAC? Source MAC is A. Now he will make an entry here on my port number 1. A is sitting. On my port number 1, the device A is connected. Correct? No, that information. Now, what is the destination this traffic should reach? That is C. How switch will decide where to forward? He will look into his MAC table. So in MAC table only information about A is there. There is no information about C. So what switch will do is, he will send it to all the ports. Okay. So what I'm talking is without a VLAN configured. Okay. So if you have a VLAN configured, then he will send all the traffic to all the ports of the same VLAN. Okay, don't add a VLAN and confuse it. So think that you have only one VLAN configured, all the ports are part of the same VLAN. So switch will send the traffic to all the ports. The data will come to device B, it will come to device C also. So what device B will do is, he will look into the destination MAC address. Destination MAC address is C. He will check his own MAC address. His own MAC address is B. That means this is not for me, right? The destination address is not my address. So this B will drop that packet. He will reject that packet, that frame. And when this another copy comes to this C, he also will check what is the destination MAC address. It is C. What is my MAC address? My MAC address is also C. So that means this data is for me. Now this C will process it. He will remove the Ethernet header, then he will see the IP packet inside that, then he will remove the IP header, then he will see the TCP inside that. He'll remove TCP, then he will see actual data, and he will process that data. Okay, so this is how the data is getting forwarded. Now, assume C is sending a response back. So what will be the frame? Source MAC address will be C, destination MAC address will be A, and he will send it out. It will come to the switch. Now what switch will do? Switch is receiving data on port number 3. So he will make an entry. What is the source MAC address? It is C. So he will make an entry. So what it says, on my port number 3, the device C is sitting. That information is correct. Now what switch will do? Switch will look for the destination MAC address in the packet, in the frame. So destination address is A. Now he will go through the MAC table. Where is MAC address A? So there is an entry in the table. So what it says, MAC address A is sitting on port number 1. Now switch will send the traffic exactly to the destination port. It will come to this device and he will process it. This is how a forwarding process in switches are happening. So in this explanation, I gave you two scenarios. One, three cases. Okay, one, how a switch is learning the MAC address, learning the information about the devices connected. How they are learning? Whenever he receives a frame, he will do the learning. He will populate the information in the MAC table. Right. Second, we saw how he do the forwarding. Forwarding, we saw two cases. One, when he sent it to that side, the destination was unknown for him, right? Switches don't know where is the destination C is sitting initially. So what he did, he forwarded to all the ports that we call it as flooding. When C respond back, the switch was aware about where is the destination. That means the destination is known. When destination is known, he will forward to exact destination port. Okay. So we depends on what is the information in the MAC table. Switch will do a flooding or forward to the destination port. Okay. And how he do learning? Whenever he receives a frame, he will make a entry in the MAC table. Yes, you got it? Any question here?
No, sir.
Bye. So this is the basic networking concept. There is nothing new I taught in this slide. Okay, this page. So why this learning is required? This will make your network performance better. Why? When he know the destination, he will just forwarding it to the destination device. He is not disturbing other devices. Otherwise, what happens? All the device will process, then they will drop it, then it will take more right processing time for that device. So those all can be optimized when switches doing the learning process. Right. So this is how your normal switches are working. Now, similar to this, how it is happening on a NSXT in the segments, how it is happening. This is much more easier. Okay, so assume this is segment 1 inside 2 nodes. Now what you are doing is you are connecting a VM to the ESXi. This MAC address is X. You are managing everything through vCenter, right? And your VM is part of your ESXi, which is actually managed by ESXi. Your segment is also running inside your ESXi. So when you connect your VM to the segment, ESXi will give the details. What is a VM's MAC address? And the segment will put that into the table saying that, okay, X is connected to my port, or maybe some 5, port number 5. Similar to that, he will put the information in his table. Okay, Y VM is connected to my port number 10. So whatever device is connected, they need not to wait for any traffic to pass to make entry in the table, because as your segment and your VM, everything is managed by ESXi. That communication is already happened when you connect the device itself, right? Now, but this ESXi, this segment is not aware about the MAC addresses of VMs connected on another device. So what happens is, for that they are following a process. To learn the MAC address of other devices, they are following a process. It is again learning only. So how they will learn is, 1 second, I'll tell you.
We are unable to hear.
Yeah, 1 second, 1 second. So every device will have a VTAP, right? So these devices need to know two information. One, they need to know if the device is connected locally, they need to know the VM is on which port or which NIC it is connected. If the destination is on another host, then he need to know how do I reach that host. So that is
Logical routing. Router. Shikmar? Hello?
what happened? You just got disconnected.
Yeah.
Okay. All right. So what happens is you have your NSXT controllers when a ESXi or when a segment learns the directly connected VMs and he populates the information into the MAC table, he will forward that information to the NSXT manager. Same way, this table also will be forwarded to the manager. Now what manager will do? He will share this information between these devices. So he will have information X is on my port number 5 and Y I can reach if I send it to TEP2 IP. He will have information Y I can reach if I send it to VTEP1 IP. So like this, all these information will be exchanged between the devices. That synchronization is done by your NSXT manager. So what is the difference between your physical network and logical network? In your physical network, you will have the MAC table populated only when there is a communication happens. But in your NSXT environment, before any communication happens, every device will get synced between them. Everyone will be aware about all other devices in the network. So there is no performance impact. There is no duplicate copies sent. There is no flooding, right? So any time when traffic comes, devices are aware where to send and they'll forward to the devices. Clear? Any question here?
No. So NSX manager also the traffic will go via NSX manager.
No. I just talked about the tables.
Hmm.
Tables are your control plane information.
Hmm.
Okay, so control plane information is exchanged through the NSXT manager. But when data comes in, data will be, as we discussed before, data will be, they'll be refer this MAC table and they'll decide whether I need to forward it to the another port on the same segment or I need to send it to the other VTAP.
Hmm.
So the traffic will just pass like this, but your control plane information is exchanged like this.
Hmm.
So once it is exchanged, after that, if your NSXT manager goes down, also there is no problem because they all have all the information. They can continue their communication. NSXT manager is not involved in any of your data forwarding process. Clear? Okay. So your devices maintains different tables. Okay, your NSXT controller or your NSXT manager maintains a global MAC address to TEP information. Right, that information helps the devices to reach other device on another host. Then there is a global ARP table, which is actually MAC to IP mapping. Okay, so these two informations are maintained in your NSXT manager. That is synchronized between the host from your manager. So there are two-way communication, right? When they learn something new, they'll send it to manager. Manager will send it to others. Same thing. They'll exchange between them. So this will ease our process for data forwarding process. That is all about our tables. So now there is another question. This information, who all nodes will share? I told you about segment. I told you about transport zone, right? So when we associate this segment to a transport zone, who all are the host part of that transport zone? On all those hosts, we will have that segment visible. This table also will be shared among those hosts. So if I have a segment 2, which is under another transport zone, then the table MAC table information of this transport zone or this segment will not be shared to these hosts. Not required, no, because this segment is visible, right? Which is available only in these hosts, and this segment is only in these hosts. Why a MAC address information of this segment need to be given to this host? Not required, because there is no communication between segments. So different segments MAC table informations or ARP informations will be isolated, or it is separated from a different segment and corresponding host. Okay, it is again similar to your VLAN only. How do I say? Wait. So on a switch, if I have MAC table, I told you it will make an entry of VLAN number and MAC address. There is additional information also there, VLAN information also there. So 2 is C, VLAN 10, and port number 3, MAC address D, VLAN 10, and port number 5, MAC address E, VLAN 20, 6, MAC address F, VLAN 20. Now, whenever a device receives a frame and he see that it is coming from VLAN 10, he will only refer all the entries for the same VLAN. He will not look into these informations, right? This will reduce the table lookup time. It will improve the performance. Similar way, in NSXT, this information of one segment will be shared to another host which is part of the same segment. Otherwise, they will not share. Okay, then what else I need to talk about?
I think we can meet on Monday.
Okay.
Tomorrow
Uh,
also.
table. Okay, 1 second. Okay. So we discussed about the forwarding on your segments, right? Host 1, host 2. We have segment 1. We have segment 2. So now if I have a unicast traffic, if MAC address A is sending something to B, then this will go through the switch. You know where is the destination? He will use the destination device's MAC address, then it will forward to there. Okay. But what if it is a multicast traffic or a broadcast traffic? Multicast traffic means one person sending to multiple destination. So I cannot use any one of these VTAP IP address as a destination, right? Because the destination may be spread across multiple hosts possible. Same case with the broadcast. Broadcast means I'm sending something to all the devices in the segment. Again, the destination may be in multiple places. To handle these scenarios, we have two choices. One is head-end replication. Second choice is two-tier hierarchy. What is head-end replication? The first step, he will make n copies. N copies. What is mean by n copy? N means number of TEP available in the network, VTEP or TEP. Right? So how many are there? 1, 2 are there. So he'll make 2 copy and he will send it to those destination devices. Now what is the problem? If your network is big, then this device will get overloaded. Correct. You need to make so many copies and send it. So alternate option is two-tier hierarchy. If your network is big, normally what we will have is we'll have a rack, we'll have a rack, we'll have a rack, subnet. Each rack will have their own subnet. So now on each rack there will be someone called a what is the term? Hmm, MTUP, I believe. I think the term is MTUP. Okay. One device will be elected as a sorry.
It's a multi-tap.
Ha ha. Right. So one device will be elected as MTUP, and this device when he send it, he will make copies for all the MTUPs. So here in this rack I may have 50 servers. That means 50 taps are there. Here also I may have 50 servers. That means 50 tap. But I will send only to the MTAP. Here also I will send. Here also I will send. My duty is over. Now what this MTAP will do is he will make copies for his all local devices. This MTAP will make copies for all his MTAPs, all his taps. So his load is now distributed to different devices, right? So instead of he making 100 copies, now he is making only 2 copy and they are making 50 copies. So he is not overloaded now. So this is the second method of right sending this multicast or broadcast traffic. This is called two-tier architecture. So these are the two different ways of handling multi-destination traffic. What is multi-destination traffic? Multicast and broadcast are called as multi-destination traffic, or we call it as bum traffic. Okay, broadcast or unknown multicast also processed similar way. Okay. All right. Sorry. Broadcast, unknown unicast, and multicast. These three are called BUM. Broadcast, unknown unicast, and multicast. These all are processed in these two methods. Okay. So that's all the theory part of your segment. Now we will see how do we uh, do the segment creation. It is very
Yes.
straightforward that we will do directly in the lab. Okay. So we create a we create a segment, then we'll associate with a transport zone, done. It's very two-step process. And how you connect your VM to a port group, exactly same way you can go to the virtual machine, right click, edit settings, you can connect, right, a network, you can click on the drop down, you will see this uh, segment also, you can select that segment and it is connected, that's it. It's not complex. Okay. And then what else? So once you connect it, then it will function similar, exactly similar to how you do it on a or normal vSwitch or DV switch. They'll talk to each other. Nothing complex. Okay. All right. So that's it for today.